So let's start by looking very briefly at what the RTL for our code looks like. Like I said, most of the RTL is probably already familiar at this point, right? So I'm going to focus only on the differences. What we have is the smart timer, right? And you can see that it has the standard set of inputs, the registers, the AXI handshaking, everything, all of this is exactly the same as what we have done earlier while implementing the AXI bus interface, right? And the only real differences that you can see over here are going to come much later. As I showed in the example, right, there is this line out here corresponding to the status wrap, right? We have this entire line corresponding to how the status wrap by itself is going to be set up and so on, right? And further down over here in the logic, we have the part which basically tells us that I can, so in the status wrap, I can see how the status wrap part of it can be cleared by writing to the status signal itself, right? And if we go further down, what we can see is, you can read out the control status and so on, the wrap pulse itself is generated, and the IRQ out is essentially connected out here as being connected to the status wrap signal itself, right? And what you can see is right at the top among the ports, we have the IRQ out as an observable output of this particular RTL code. Right. So what we can do with this is, of course, I have a CocoDB based test bench, right, as before for this, right. If I look in this, there are the tests, and if I run make, it essentially goes through and runs the simulation using the Verilog simulator, right. So why am I using Verilater over here? Because like I said, there are two open source simulators for Verilog that we can typically use over here. One of them is the iVerilog, right, which is probably slightly easier to use. Verilater on the other hand has a couple of nice features. The most important one as far as we are concerned is the fact that we can actually use it for co-simulation with Reynode. So I want to make sure that this passes a Verilation simulator, right, a Verilated simulation. And we have some 4 tests, right, all of those pass over here. You can very quickly look at what those tests are as well, right. These are the typical, the AXI tests that we have been already, CocoDB based tests that we have been looking at. For example, over here I am not looking at generally whether the smart timer works in the first place. I want to specifically test things about the IRQ, right. So the way that I do it would be, for example, I give it a relatively short period, assert that start the counting by enabling the timer by writing 1 to the control, wait for some number of clock cycles which is sufficient for it to wrap, and then check that the IRQ out dot value is equal to 1, right. Similarly, I can then also check that the status wrap itself should be set at that point. I can also check that after this happens, when I write 1 to clear, it actually gets cleared as requested, right. In other words, I verify that the IRQ goes high, I write 1 to the status offset to clear it, and then check that the IRQ goes low. So there are a few tests of this sort that we can write, which makes sense. All of these tests are focused directly on the IRQ behavior, not in general on whether the counter works, right. But as you can imagine, that's just for my demonstration purposes over here. In general, when you are writing a system, you are testing all parts of it. Is the counter working as expected? Does it respond properly when you start counting? What happens when you reset? What happens immediately after reset? What happens if you start counting, then stop and then start again? And then of course what happens when the IRQ is generated, right? So there will be a fairly large number of tests that you would typically write. What I have shown over here are just something very specific for the IRQ alone. Right, so that part of it takes care of the RTL code itself. We now have to make some further modifications to that RTL. We basically need to sort of have a wrapper around it, right, which is used for the Verilation for co-simulation with Renode. And just like we saw in the case of the FIR filter, right, there is the simmain.cpp where I am basically going to show you what the code corresponding to this looks like, right. So what we have is a very simple type of code out here, right. This is largely based on an example code for the fast VDMA, fast video DMA example, which comes with the Renode example code itself, right. So Renode has this thing called the Verilator integration, and as part of that they have basically provided some example codes for one of their sort of demonstration cases, which is a DMA module for video memory access, right. So what I have done here is I basically adapted that for our requirements, and this is the code that we see over there, right. It's also very similar to the code that we have already seen in the other examples, so I'm not really going to focus much on that, except for a couple of things that are worth sort of pointing out. One of them is the fact that I explicitly need to register the interrupts that we have out here, right. So I am basically saying in my co-simulation, take that signal IRQ out and map it as one of the signals, right, which is actually going to be seen as an interrupt signal, right. So in my Renode, in the REPL file, when I finally do the mapping saying 0 maps onto GIC at 33, right, it's going to take the signal that I have over here and connect it up in the appropriate place, right. So some amount of setup is required even in terms of the Verilation top level file. So we need to sort of set things up properly to make sure that our simulation is, or emulation is going to work correctly. Now, like I said, at this point I am going to be showing you a very simple form of the driver, right. The driver over here is largely the same driver as what we have for the previous examples of the smart timer. The main difference is going to be this particular function right here, right, which basically says static IRQ return type, right. And as you can see over here, it has certain things. It basically takes in an IRQ number and it needs to be registered appropriately. How is it going to get that IRQ number? All of that comes from the device tree, right. So we don't need to hard code anything in here. We write the interrupt handler assuming that the information about what is the number of the interrupt, how it should be handled, or rather, how are things connected up and so on, is handled at some other level. Somebody provides that information through the device tree. From the device tree, the kernel basically is able to extract that information and give me whatever info I need through some suitable data structures, right. And the interrupt handler right now is extremely simple. What it does is it currently just reads the existing status offset, and then it goes here and you can see that there is this line which says increment the IRQ count, okay. And you will notice that there is this thing which says atomic underscore inc. Atomic increment basically means that I want to make sure that while I am modifying this, right, so there is a problem when you are trying to, let's say in C, even if you write a simple statement like x is equal to x plus 1, right, potentially you have the danger that, after all, how do you do x is equal to x plus 1? I read the present value of x into a register, I add 1 to it, and then I write something, I write that result back into the memory location, right. Now here's the catch. It is possible, especially in a multiprocessing system, that in between the time that you read the value of x and you write the new value of x back, there was another process that also tried writing something new into the value of x, okay. So you do not want such a race condition where two different pieces of code from two different processors are trying to modify a given memory location at the same time, right. So to avoid that, what we do is we use this concept of atomic operations. The atomic operation over here basically says that while I am trying to modify IRQ count, no one else is allowed to access it, okay. So we ensure that even if multiple interrupts are coming and they are being handled by different processors and so on, this thing will get incremented only once, or rather it will make sure that at any given point in time only after my handler has finished incrementing can the next one go in and increment again, right. You will also notice that there is a line after that which basically says dev info rate limited, which basically prints out something like timer wrap and how many times it has managed to wrap the timer around, or how many times this interrupt has got generated, right. So in other words, this IRQ count, right, this variable that you can see up here, right, is just keeping track of how many times the IRQ occurred. So like I said, this is a very simple kind of interrupt handler. It's not doing anything useful other than just telling us that this happened. This dev info rate limited is interesting because what it tells us is, yes, it is going to print something into the kernel logs, but the reason why it is rate limited is because remember that we are dealing with an OS kernel. It is possible that by just sending too many interrupts, we can flood the kernel with so many messages that it's not able to do anything else, it's not actually able to do work. So the kernel provides mechanisms by which it can automatically make sure that if the interrupt is occurring too many times or too frequently, it will basically just say, okay, it happened too often, I'm not printing all of those things out. Okay. The important part of course is we need to clear the interrupt, right. So remember how the software has to handle clearing the interrupt, that's being done by our IRQ handler. So that's basically it. The rest of this device driver is more or less exactly the same as before, right. We have the control show, control store, everything exactly, basically these are the attributes that go into sysfs, and we will see how they work shortly. Alright, so now we are close to looking at the actual Renode based demo. There are a couple of things we need to keep in mind over here. One of them is, what does our device tree itself look like, right. So I'm going to look at the DTS file. Once again, this is pretty much exactly the same as before, so I'm going to go straight through and look only at the part corresponding to the AXI bus. And as you can see over here, the smart timer entry corresponds what the compatibility flag, the register ranges, and the two new lines, interrupts and interrupt parent. Now, as we can see over here, this interrupt parent number is pretty much common to all the values that we have, right. And why is it this number 4? You can see that it basically has this number 4 over here, and it so happens that if we go and look for the P handle, right, which is basically the pointer handle corresponding to this, the interrupt controller device in the DTS says that its handle is 0x04, which is why all the other ones that are connected to this particular interrupt handler give this number 0x04 as the parent, interrupt parent, so that they are pointing to this particular interrupt controller. Okay, let's get back to our smart timer. Yeah, now the interrupts itself, like we said, right, there are these three parameters that need to be provided. The first is 0, which corresponds to the GIC SPI, the shared peripheral interrupt. Okay. This last one corresponds to 0x04, which is the level triggered active high. So both of these are standard. And then in the middle we have 0x21, which is decimal 33, which basically says that we are on shared peripheral interrupt number 33 and it is level high, level triggered active high interrupt. Okay. So that is what is being specified out here. So what do? We have to take this device tree specification, the DTS file, and compile it into a DTB file, right, using the DTC command, right. So standard stuff which has been done in previous examples, and the output of that is basically stored inside this bin files directory. Okay. What else do we have? We also have an overlay, right. Oops. We also have this overlay which is part of the REPL, the Renode platform description given to Renode, right. And as I described earlier, it basically says that this is a co-simulated peripheral, right. This frequency number is something that we can play around with. We can basically choose it in such a way that our simulation runs fast enough, but at the same time it does not lose too much information that we need, right. Why is this needed? Because if I make this number too high, then it would pretty much mean that for every cycle that is happening or every instruction that is happening inside the CPU, the entire peripheral needs to also get simulated in RTL, right, and that can slow things down way too much more than what we would like. This cosim to renode maps the IRQ as GPIO, which can actually get as the IRQ out signal, which can actually get mapped onto the interrupt controller. And this line out here, right, basically tells us that take the signal, right, which is coming out of the co-simulated peripheral and connect it to the GIC at signal number 33, right, which basically corresponds to the GIC input 65, as we will see later. Okay. Alright, so we have everything set up over here. I have already compiled the kernel and put in the device driver into the appropriate location, right. So you still need to go through that, you need to compile the kernel, you need to make sure that the device driver goes into the appropriate place in the initram FS, all of that needs to be done. And then our renode demo actually sets things up by saying, okay, point to that kernel image and to this device tree blob and let's boot. Okay, so I am going to go ahead and run that now. So we have started things up, right. I am going to just add a piece of logging information over here, right, so that I log all peripheral accesses to this and basically say that any access to the smart timer peripheral which is there inside my system, just log it on this screen, you know, the green sort of signals that are coming along at the bottom over there, right. So let me just get rid of this one and bring up my UART1 instead and go ahead and start the simulation, right. And this tends to take a little bit of time, right, simply because it basically requires you are after all emulating a fairly slow system out here, right. But as you will see, eventually at some point the entire system will boot up, we will be dropped into a shell where we can start typing commands. So let's just get to that point. Alright, so you would have noticed that, you know, this takes a little time to boot, but eventually we get to this point where we now have a shell interface, right, and we can type commands over here as usual, right. We can basically, this is a regular Linux system. Now what I am going to do is I am basically going to go into the sys file system, right, and you can see that there is already this thing over here saying that there is a smart timer device, right. And the reason why it shows up over there is because it's already been mentioned in the device tree. But if you go inside that particular folder and you look over here, you will see that it actually doesn't seem, something doesn't seem right, right. In particular, it doesn't have those files corresponding to the control, period, offset and so on, which we expect. And the reason is simple, the driver has not been loaded. Okay, so the device tree knows that there is such a device, so it created something on the sysfs for you, but it doesn't have a driver, so it doesn't actually know what attributes need to be sort of exposed to the /sys file system. So let's load the driver. Like I said, I have already sort of compiled it and put it in there. So I will need to do this mod probe command. And you can see that when I do the mod probe, it basically gives me this message saying loading out of tree module, etc. Okay, that's fine, you know, I mean, I wrote the module, therefore it is still out of tree. What does out of tree mean? It basically means that it's not part of the direct Linux kernel source code. It was written by somebody else, right? So in other words, the people who have set up the Linux kernel are not going to guarantee the functionality of this module, which is understandable because after all I wrote it and I have nothing to do with the Linux kernel maintainers. Interestingly, yes, it probed, it found out that there is this particular thing at 0x7, the same address. Now you might notice that it also showed you something about an IRQ number, okay, and this was not there earlier. It has registered an IRQ handler, in other words, right, but you will notice that this number IRQ42 doesn't seem to have anything to do with the numbers that we have talked about so far. What we said was basically 33, right, is where we are connecting it, and that in turn gets connected to 33 plus 32, so 65 on the GIC. So where did 42 come from, right? Turns out that is just an internal number which the OS generates for every new device that's getting connected. But one thing which is very useful in terms of debugging also for us is that there is one more virtual file system called /proc, right, and within that there is one particular file called interrupts. If we look at it, right, and let me just maximize this window here to make things a bit more clear, you can see that it actually contains a list of all the different interrupts that are present on the system. Okay. There are a few things such as the watchdog timer, the UART and so on, which you can see are actually already generating interrupts, right. So a fairly large number of interrupts have already been generated by those things. There are a number of different interrupts generated or rather connected to things like the DMA controller, but they are not really active, as you can see here. There are 0 interrupts generated from them, right. And here you can see that number 42, right, corresponds to this smart timer that we have just attached, the driver. And here in fact if you look at it, you will see that this number 65 finally shows up, right. What is this number 65? That is the actual GIC SPI value, right, the interrupt number, right. We specified 33 within the SPI range, so it adds 32 to it, gets the number 65, and therefore it tells us that this is interrupt number 65. Okay. So this /proc/interrupts is very useful when you are trying to debug something corresponding to the device, right. Alright, so let's proceed. So far it does not look like there are any interrupts because you can see that this number of interrupts out here is actually 0, nothing has changed, right. So I am going to start off by putting a fairly small value into that period number, right, because I wanted to sort of at least generate interrupts at a reasonably at something that will allow us to actually at least see that the interrupts are getting generated. Now it turns out that because of the way Renode works and the way that the Renode clock interacts with the system clock that is being used for the RTL, the numbers that you give over here and how frequently the interrupts get generated will not really be closely correlated, right. So there will be some discrepancy, you won't find that it's matching the way that you might expect. All that you can hope for is that you see that yes, there are interrupts being generated, right. So how do I even get something like this to work? The most important thing is I need to give a number, right. So let me give something like 5000 and write this into my period variable, right. And in fact, yeah, you might notice that as soon as I loaded the driver, all of these things, the control, duty, period and so on, suddenly appeared in this SFS, right. They weren't there before, but when I loaded the driver they appeared, which means that I can write something to the period, I can check the value out there, right, and yes, it has, of course this is showing it in hexadecimal, but that's the value that's there. I can similarly write something, let's say 1000 into the duty register, right, and sure enough it shows that in hex, right. Now what I need to do is basically just write 1 into my control register, right, and you will notice that nothing much seems to have happened, and the reason for that is because the system is fairly slow. It takes time to respond, or rather it takes time to actually simulate what's going on behind the scenes. But after a small amount of time, you will notice that this message comes up over here, right. It basically tells you that the timer wrap IRQ number 1 occurred, and after a short while, without my having done anything, right, it prints the next message saying timer wrap IRQ number 2. And if I wait for sufficiently long, it will continue showing me these IRQ wrap numbers. Why is this happening? Because my device driver had that rate limited info message that it was printing out, which gets printed out onto the console over here, right, which shows me the present value of the number of IRQs that have been received so far, right. The interesting thing is you can also correlate this by looking at /proc/interrupts. So you can see that by looking in /proc/interrupts, the number of interrupts that have been received so far is getting reflected out here. This value basically shows up as 4, right, and since then of course a couple of more interrupts have happened, so it basically continues going up and now the value has become 6, right. If I look at the value of the status register, I'll find that it basically is always showing me 0, right. And this seems a little surprising because after all I do expect that the status does wrap around and so on, but the point is it's automatically handled by the interrupt controller, right, the moment, or rather the interrupt handler. The moment the interrupt occurs, it basically goes in there and clears the interrupt, right. Now by writing 0 into the control register, right, I can actually make the system stop and no further interrupts should occur, right. So if I wait for sufficiently long, I should find that it basically remains stopped at whatever was the last value of the interrupt counter that I saw, right, until at some point I then go in there, once again write 1 into the interrupt controller, and I can find that once again interrupts start happening, right. This can be useful in a number of different ways, including in practice, right, on a real hardware system. One of the things that I could do could even be to have some kind of a free running counter, just something which is keeping track of how many clock cycles have elapsed sitting inside a particular piece of hardware, and just reading that back and saying, okay, this is the time as far as the hardware is concerned, this is how much time has passed, right. So the purpose of this demo, as I said, was not really to show you how to write the device driver, but to basically take a very simple example of a device driver and just demonstrate that I'm able to modify the RTL, get an IRQ signal, connect it up to my GIC, make the changes in Renode as well as in my DTS as well as DTS so that the entire system reflects those changes, and write a very basic minimal device driver that responds to these interrupts.